All right, we'll just jump straight in. I'm sorry about the logistical problems here. Simon Clark, I'm on the same team as Arnab on the development side, and we own the development and evolution of the FSSHTTP protocol, which is unfortunately a mouthful. I want to try and not jump into too many sort of low-level details sort of on my own. If you've got questions, I can sort of direct my talk as necessary. I find that's a much easier way because there's a lot of scope to this protocol and a fair amount of complexity. Unfortunately, we think it's necessary complexity, but it's there nonetheless. So I want to talk just a little bit about what it is, some of the documents we have for you guys. So there's 3, and I can talk about what you'll find in each. And then jump into a little bit of the more complex aspects of it, particularly around how we synchronize data and some of the sort of aspects in there that are potentially interesting things that can be leveraged by our partners. And just walk through a sync example and then hopefully leave time for questions so that we can jump into anything that I haven't covered. So, I mean, I think this has actually been fairly well covered over the last 2 talks. We used to use FPRPC, which is basically just HTTP-based, full file access. So it evolved to DAV, which is effectively the same thing from all intensive purposes, where you open a file, we download the whole file, put it in a temporary directory, Word, Excel, PowerPoint, open it from there, make necessary changes, you hit save, it goes back into the temp directory, upload the whole file. And that's nice and simple, but it's not very efficient from both a bandwidth perspective, a server perspective, as we get all of the, as we get a 20 megabyte or so deck back up there, we have to reprocess and restore the whole thing. And so when you start to look at more interesting scenarios around collaboration and multi-user authoring, we want to be doing that load and save, obviously on a high frequency basis. And the more we do it, the more stress we put both on the network infrastructure and on the back-end servers. And so what we were after was a new way of synchronizing the data so that we could do it based on the size of the user's change rather than on the size of the actual file. And I mean, the PowerPoint example is one of the most obvious that comes to mind. You can imagine a huge deck, but you've only got changes occurring maybe in a very localized portion of even just a single slide. And so there's no reason why all of those movies and template images should be traveling back and forth. And so that was the genesis of the need for this new protocol. Once we started digging in, there was the data sync aspect, but we also found we needed a number of new facilities for controlling and signaling of the multi-user and the co-authoring data. Show where people are in the document, list of editors, a lot of other services. And so I should go to the next slide. So we effectively started by building a mechanism that could allow us to express a series of set of different services within a single protocol. The services could be linked together, and you could make requests that, sorry, let me back up. We defined a set of services such as incremental data sync and the ability to track users' presence and roster of people in the document, and then defined a set of requests that could be used to manipulate those services. And those can all live in a single package that can travel back and forth to the server. And we can have interdependencies between those requests so that we can enable sort of more complex sets of operations. And so at its basis, it's just a packaging system. And so you'll see in the first document that I'll call out in a second, that it's just laying out the way in which requests are encoded. As you look at the types of requests, you'll see that they belong to different sets of services. The ones for managing locks and co-authoring metadata are actually relatively straightforward, and as you see them in the different sections in the document, they're pretty easy to understand what's going on. A lot of the confusion comes around the incremental data sync aspect, because there are a lot of requests, and it's actually using a relatively complex data model to represent the documents. So there again, you can see you've got this package of requests that can go back and forth to the server. On the service, we actually needed to define more than just a traditional file in terms of a stream of data. And this is what we refer to as the file model. And it contains, obviously, the main content of the document, which we call a content partition. So that's the XML of the PowerPoint slide deck or the Word document. But we're also able to store an arbitrary number of metadata partitions. And these are just data stores alongside the main contents. And you can, if you think back to alternate streams in NTFS, it's very similar to that. And they're all addressable through the protocol. And we then, in the applications, define semantics within those partitions to manage the authoring. There's also some more advanced lock state that we store along with the document. So in addition to having exclusive access, there's also this notion of shared locks. And a shared lock is basically just a way of marking the document with the higher level protocol semantics that are being used to access that document. And so what I mean by that is if you take an application like Word, we define a method for multi-user authoring that puts various semantics on, say, this first partition and the second partition, and there's an XML schema that defines, you know, where users are in the document. And by taking a shared lock with a specific ID, Word is really marking this file and saying, hey, anybody who's willing to play by these rules can access this document. And that's how we can version different ways of collaborating on the same file type later as we evolve the protocols. Any questions on that just yet?
That's involved with this metadata editing from an older client that doesn't understand it.
So, good question. So the question was, what happens when we open a document just using a traditional protocol such as DAV? And the answer is that the DAV implementation will respect the locks that have been taken at this level, and then provide access to the main content partition. And so if a document is in a co-authoring session, it'll have a shared lock. You'll have clients accessing it through the FSS protocol, and when a DAV client comes along, it will not be able to take an exclusive lock, because that will conflict with the shared lock. And so it will, in effect, open it read-only against the main, and you'll get the main content stream. So it should interop, well, it does interop well. The main concern, of course, is if you open the file first from the DAV client, the exclusive lock will succeed, and then the shared locks that we try and take from the modern apps will be denied. And those modern apps will go into a read-only mode. And so we try to engineer scenarios so that we don't have these lockout situations. So sort of we covered this sort of packaging, bunch of requests that are able to manipulate to different services. Sorry, go ahead. It's on both in that so you can think that we have this file model that includes the metadata, and we synchronize that file model onto the client. From a user data perspective, the user only sees the contents of the document. But under the hood, what's happening is this metadata is living on the server. It's being synchronized to all of the clients into their document caches, and then the applications are manipulating the metadata in the document cache, and that's going back and forth. And in effect, you can think of that metadata as the signaling channel for all of the collaboration. Sorry? And, yeah. But at the end of the day, we care most obviously about this main content, because that's where the document is. And it really is it's what we call the end user file format. It's the OPC package with the XML, and it's normal. So we've split from the way that things evolved has caused us to layer the various the protocol into various layers, and it's documented in 3 documents. You'll find that the MSF, the base document, FSSHTTP, I can never say that, describes the request packaging mechanism. It's all encoded in XML, and you'll also find details of how the locking services and the co-authoring services work in that document. It's pretty straightforward, actually. We then have the FSSHTTP document, which is the request packaging specifically for the file sync part of the protocol. It's binary. There's a binary encoding for that. We chose binary because we have a lot more constructs and primitives within the protocol at this level, and we couldn't afford to have them encoded directly in XML from an overhead perspective. This is where a lot of the meat is. You'll find, because not only are we describing the binary encoding, but we're describing the actual data model for representing these incremental changes. And we'll go into an example quickly in a moment. The FSSHTTP document describes how we use the data model for incremental sync to model traditional files. So that's our Office documents, it's zip files, which are the base of our Office documents these days, and actually any other file that we need to synchronize. As Arnab showed you in the SkyDrive and SkyDrive Pro demo, you can drop any, we can support the synchronization of any file in an arbitrary file system folder, and so we want to be able to do that in an efficient way. Any questions on that so far? Okay. So we'll dive a little bit into the data sync portion of the protocol. So you'll see in the documentation this layer is referred to as the self-storage layer, and that's it's. I wanted to try and avoid going too deep into the details, but the model is comprised of a set of entities that we call cells, which represent units of consistency within a file, pieces that have to change atomically and in a transactional way, and objects under those, which are the units of change within the protocol. And you'll find this documented in the B document, but that's where the term self-storage comes from. And so sort of at a high level, you'll find that a given file state, a given document, is represented as a directed graph of nodes. And any change to the document is a change to a set of nodes in that graph. And then synchronization is the process of exchanging nodes and edges that have changed between client and server. That's sort of I think, as high level as I can put it. And what we aim to do is create a schema in that graph that maps as closely as possible to the expected change that we see in our applications. So an example is that you might have, sorry, I don't have a diagram for this actually. We might have a set of nodes in a graph for a PowerPoint deck, and maybe there's a root node for each slide, and under the slide there are nodes for every object on the slide. And maybe you make a change to just one outline. That would be a change to just one node, which means that the synchronization only needs to move that node back and forth between client and server. And that's the way that we achieve the incremental sync. So if you look in MSF SSHTTP, you'll find, as I said, the schema in that graph that describes normal file stream-based documents. So OneNote acts a bit differently in that they, instead of using a traditional file format, they integrate directly with the protocol or the file model. And the MS-1 document describes how they represent the notebook, sections, pages, objects on the pages directly within the graph. And you'll find there's 2 very different ways in which we use it. I just sort of wanted to show you what we do with an actual zip or OPC file. So I'm sure you're familiar with the open packaging conventions that we use as the basis of the Office file formats. They're effectively just zip files, and the way that we structure the the contents of the document in those zip files maps very well to sort of discrete units of change. You'll find a slide is comprised of a set of zip items. They're called package parts, but zip items under the hood. And the elements within a slide then map down to more zip items. And so what we do is we take that zip file and we chunk it into a set of chunks that are then represented in a graph. Actually, it's a tree structure that then mean that as user edits happen, they're only tending to touch the nodes that correspond to that piece of data. And then we give it to the protocol, and it can synchronize back and forth. Similarly, for all other files that we don't understand, we use the RDC algorithm from Windows that is able to basically take an arbitrary file. It runs this algorithm they call filter max on it and creates split points, and those split points are arbitrary. Sorry, we give the algorithm a target size for those for the chunks. I believe it's 16 or 32K, and the algorithm is trying to identify stable points in the stream that will tend not to move as changes occur upstream. A great example of this is you could imagine an algorithm for text that chunks based on paragraph marks. And so if I insert some more characters at the top of a document, I don't change where all those paragraph marks are relative to the contents around them. And that's how we're able to efficiently synchronize files that have had inserts and deletes in the stream data. You can find more information about that in the Windows remote differential compression documents. And we actually link to them from the FSSHTTP document. And as I say, the main scenario here that you'll find is when the SkyDrive and SkyDrive Pro clients are running against the server that supports the FSS protocol. So this graph, any questions so far? I just want to make sure we don't leave anything behind. Yes? So the question is, does RDC have to have knowledge of the schema of the file? Or, no, it doesn't. Again, because it's a statistical chunking process, so it's only trying to determine chunks of an average size, an average size. So it's aiming for, say, 16K chunks through the file, but instead of choosing those boundaries based on static points or offsets within the file, it's using a statistical signature that is trying to remain constant. It's always difficult to describe, but it's looking at the data. It's looking at the data around a specific point to try and identify that point. So it doesn't really need to know the schema, and it's not really doing. It's sort of tempting to think that it's sort of using some magical, process to determine like points based on the type of the data, but it's just statistical. So I'm not answering the question very well, but no, it doesn't. So the graph I'm talking about, you'll hear in the documentation is referred to as the way we talk about it is known as this data element graph, and it's a graph of two types of nodes. One is these things we call data elements, which is the majority of the nodes in the graph. They're interesting because they carry data and they're immutable, and they're identified by a GUID. And we then sprinkle throughout the graph in the graph schema a type of node we call index nodes, which are much smaller. In fact, they're just key value pairs, so they're effectively edges in the graph. And those are the mutable entities within the graph. There are only a couple of places in which we have those in the topology. So the majority of this graph are these data elements. There are different types of data elements, but at the end of the day, they all carry a specific type of data. Some of that's user data, some of it's metadata, and they have this immutable property. So the process of sync is all about that data element graph and just exchanging and synchronizing the state of the data elements and the index nodes between them. It's really easy for the data elements because, again, they're all immutable. They have stable, globally unique IDs. So the process of sync is basically to ask a server, hey, I have this set of data elements. Give me all the ones I don't. And then the complex piece is just dealing with those index nodes, which are mutable and need some basic tracking. But they end up being key-value pairs, so it's relatively easy to exchange and reason about them. Our servers tend to implement that graph as a blob store and a key-value pair store. And so at the end of the day, the blob store is easy to manage because of the immutable aspect of the blobs, and the key-value pair table tends to be small and, again, easily manageable. And so sort of an abstract example here is it's a graph that has a couple. This is not our schema, but it illustrates the point, where we have a couple of index nodes pointing at these data element nodes, the data element nodes being the immutable data. And say I've got this graph on the server, and my client wants to download it. So the client makes a request. It's called a query changes request, and it says, hey, give me all the changes that I don't know about. And in the process, it passes its current state. Well, its current state is nothing. So the server enumerates, walks this graph, and determines the client doesn't have any of these nodes, so sends the entire plane. There it goes. So it sends the entire graph over to the client. Client's now got this graph. If you imagine that looked like the one I showed you from the zip file, it can now traverse this and render the file and show it to the user. So then say somebody does an update to the server gets updated with a new set of changes. So you can see that we've changed the index node. We could do that because it was mutable. We've added a new data element node under this index node, which points to another one, and so on. And we've got some new content. So again, the client learns that there's been a change on the server by polling it, and asks the server to enumerate any changes and send them back. And when it does this, it sends its current state to the server, and it can describe the current state based on the IDs of these data element nodes. And we have an optimization that, again, described in the protocol documentation that, on average, tries to arrange those IDs to be in sequential order. I said they're GUIDs. That's actually just half the story. They end up being GUIDs and integer pairs, and together that GUID integer needs to be globally unique, which is easy to arrange. I mean, you can always just generate a new GUID and use one as the integer, or if you know that you're the only one using a particular GUID, you can sequentially allocate GUIDs. We try to arrange that. It's not actually required, but the more we arrange that, the more compressible those IDs become. So describing my current client state becomes as simple as saying I have all nodes 1 through 6. And that's a very concise representation that can be sent to the server. The server then walks this graph again, and of course, anything that, as it encounters nodes, it can now tell whether that client has them or not, and of course, can send them back. And so now the client is back in sync. And this makes sync reasonably simple at a high level. It also makes managing merge and conflicts easy, because data elements, they're immutable. They can never conflict. If I have one, or if I know another client has one, then I know exactly what state we're talking about. And we only have to manage it at the index node level. And there are very distinct rules for doing that, again, spelled out in the documentation. So kind of what does all of this mean practically? I think the most important thing is that the protocol, though complicated, at the end of the day is just a set of requests that are reasoning about these services. Some are really simple. The locking, there's a request that has no arguments that gets the time on the server. or asks who you are from an authentication perspective. Then the main complexity is within the requests for managing file sync. At the end of the day, file sync comes down to these data elements and these index nodes. The index nodes are relatively constrained within the system. Data elements are where all of the main it's where all the user data lives and moves around. They're immutable. They have stable, globally unique IDs. So you can almost think about them as, at a very high level, that a file is comprised of a bunch of subfiles that have GUIDs, and that you can address that file at that level. So those blobs, the data elements that map to effectively our blobs, make are very useful in terms of caching and from a deduping perspective, because the whole point of the protocol is to transfer and reason in the smallest number of blobs possible. So as you make changes, it's effectively a copy on write system. So that's a thing that we can leverage, and we do leverage within our systems. It is important that things like the IDs remain stable. So if you're manipulating the protocol, at the end of the day, as long as the IDs that the clients are reasoning about are the same, everything should work. If they become skewed or they're changed, you'll find that scenarios start to break down as conflicts are introduced, and either sometimes the apps can't resolve the conflicts, or you get very undesirable results. The other thing I sort of wanted to touch on is that, because again, we're incremental, it sounds obvious, but it's sometimes sort of overlooked. It's very hard at points in the system to determine the whole file state, because you're only seeing the incremental pieces go back and forth. And you're only seeing them go back and forth at the level of this graph, so sometimes it's hard to even reason about what part of the document is changing, because you just don't have the context around that change. So that's kind of what I wanted to touch on. Do you guys have questions? I can go into more detail on specific things if there's any area that I've brushed over too quickly. No? The question is, it seems like there are many scenarios where you want to reason about the entire file, and is that weakness of the protocol? There's nothing. So the clarification was more about if you're just looking at traffic go back and forth, that you can't determine the full state of the file because we're not reasoning about the full state of the file, and that's sort of a natural consequence of being incremental. If you need the whole state of the file or need to do something with the file, you can either make a direct traditional WebDAV call to get the file, or you can actually leverage the protocol to do it incrementally. So we've had situations where we want something to be able to parse properties or reason about the file as it changes. And there's nothing to stop a client acting as a sync agent that every time there's a change, it's picking up those new changes. But it's always doing it based on state it had before. You need that state before, or you need to get all the state. You can't just see the individual packets go over the wire and then get the whole document. So it's possible. It needs. It's just easy to. We've had problems internally where it's easy for people to sort of fall into the trap of, oh well, I'll just, if somebody's making a change, we just want to index the paragraph they changed, and it's sometimes tricky to do that because you might not even know that it was a paragraph because of, if it's one character just going back and forth or something, that it can be very hard to get that context. Does that answer the question? Okay. At the end of the day, if you need the file, and actually if you need the file with no previous state, and you're going to do something with it, maybe A/B scan it and then be done, the best way to get it is with DAV. That's what DAV does well, and you should use it. So. So the question is, if you do want the full state, do you use WebDAV to? Oh, and then keep in sync. Actually, that's a good question. So, do you do a WebDAV call and then use FSSHTTP afterwards to keep on syncing it? The answer is you should. If you're going to keep on syncing it incrementally, you need to start with FSSHTTP. And the reason is because WebDAV doesn't have all of the sync metadata. And so the first time you get it, yes, you'll get the full file. And if that's all you needed and you're never going to get it again, that's perfectly sufficient. But if you then want to come back and ask for more changes, you need to be using the protocol so the server knows what you previously had. And a WebDAV is just the file state. It doesn't have the descriptions of the IDs that you had before. And so what will happen is the second time you go back, you'll get the whole file again, and then you'll become incremental. So the question is, am I aware of any libraries that can implement it? I'm not aware. I'd have to ask one of my colleagues. There may well be. I mean, it's as I say, all you could generate one from the documentation. Just exercise left to the to the reader.
We can talk more offline about that too. I think I understand where you're coming from our previous discussion, so we can follow up on that.
Yes? It is. The upload, it's actually maintained in the Office document cache, and the upload center is a UI on top of that, so yes. Question is the Office document cache available to third-party applications? It's built into Office, so it's a component of the Office suite in much the same way as any other component. So it's available in so much as you interop and build on Office as a platform. It does. SkyDrive Pro leverages the Office document cache. They work together to both provide the file-based sync and the collaboration features so that you can use them all together. I believe at the moment, Anab, do you?
I'll just repeat myself. There are no direct APIs to call into the Office document cache from a third-party application, but there's obviously an extensibility and programmability story for Office apps like Word, Excel, PowerPoint. So if you're driving those against SD Pro, you'll end up leveraging all the caching infrastructure on the client.
Yeah, I mean, you can indirectly get at it, as Arnab said, through the applications and through SkyDrive Pro. So manipulating the file system will actually cause the Office document cache to interact with that. So there are ways, but all right. Okay.